Hello everyone, this is Dr. Webb. So in this video we're going to move into a new and very important area in group theory, which is called permutations. We're going to spend a number of videos working on permutations, and eventually we are going to be proving some very important results, some of the most important results of the class using permutations. But in this video we're just trying to go through some definitions. We're not going to be really proving anything real too major. So let's start talking about permutations. So what is a permutation? So a permutation of a set A is a function from A to itself that is both one-to-one and onto. So let's say that our set A has, let's say, three things in it. Let's do a spade, a heart, and a diamond. I guess that's a club, a heart, and a diamond. No spades. And so what a permutation would be, let's call it a permutation sigma. And so we can think about it in terms of a set, kind of having our elements. And so the left side is going to be our domain. The right side is going to be our range. And so we need to come up with a one-to-one and onto function. So one-to-one, so I can do something like this. That works. It's onto because it's hitting everything in the range, and it's one-to-one because everything in the range only has one element in its preimage, right? And so we can come up with a whole bunch of different ones. We could have a permutation where everything gets sent to itself. So this would be the identity permutation, because it doesn't change where anything goes to. We could have a permutation where club gets sent to heart, and heart gets sent to club, and diamond just stays by itself. So in this, diamond would be what's called a fixed point of the permutation because it didn't change. But we're not allowed to have functions like this where hearts has two preimages and clubs doesn't have any. So this function is neither one-to-one nor onto, and so it is not a permutation. Okay, so in our talking about permutations, we're mainly going to focus on the case where the size of A is finite. You can have permutations of infinite sets, but finite sets is really going to be where we're going to be doing most of our work. And in general, if we're just talking about some general set with n elements, rather than coming up with a bunch of goofy symbols, we're just going to use the numbers 1, 2, 3 up to n to denote the elements of that set. And so really when we're talking about a permutation on a set of size n, we're really going to be talking about a permutation on the numbers 1, 2, 3 up to n. Okay, so let's let sigma be a permutation on the set 1, 2, 3, 4, 5. And we're going to define sigma by sigma sends 1 to 3, 2 to 5, 3 to 2, 4 to 4, and 5 to 1. And so we could write this out like we had before. Drawing arrows where everything is going. 3 is going to 2, 4 is going to itself, 5 is going back to 1. And we can see that, by looking at it this way, it's clearly one-to-one and onto. Everything in the range is getting hit, and it's getting hit exactly once. But it's a little bit tiresome to write this out every time like this. And so we have some shorthand notation. And so the way that we're going to express it is we're going to think about the top as being the domain or the preimages, while the bottom, this is our range. This is where things are going. So these are the images once the numbers get sent through sigma. So 1's going to 3, 2's going to 5, 3's going to 2, 4's going to itself, and 5's going to 1. And from here, this is really where you can see how we get the name permutation, because when we're doing a permutation, what we're going to, the top row, if we're doing a permutation on 1, 2, 3, 4, 5, in any permutation, this top row is going to stay the same, but in the bottom row, we're going to have some reordering of the numbers 1 through 5. And so the possibilities here are going to run through all the possible permutations of how we could put in the numbers 1 through 5 down there. Okay, so let's let sigma be the permutation we're talking about. Now let's take another permutation row. So row sends 1 to 2, 2 to 4, 3 to 5, 4 to 3, and 5 to 1. Well, once we have two functions, we can talk about combining them together. So we're going to let, if I say row sigma, this is going to represent the composition of the two functions. And in this composition, sigma is the one that's applied first, and rho is the one that's applied second. So we're writing row sigma, but in this, sigma is the one that's being applied first. And so you can think about this as this is similar to how we would write row composed with sigma. And when you do a composition like this, when you plug something into here, what really is x going into first? Well, it's first going into sigma, and then it's going into rho. And so x first goes into sigma, and then whatever you get out of that goes to rho. And so this is going to be our notation in this class. And this is the most common notation that's used for composition of permutations, although there are some books and some authors that do it the other way. But just remember that when we have a line of permutations applied together, the first one is the one that's on the right. The first one being applied is the one on the right, not the one on the left. This is actually also similar to how you apply matrices to a vector. If a vector is on the right, the matrices that get applied to it come right to left, not left to right. So we want to see what our permutation is when we apply sigma and then rho. So just to be clear, sigma, this is first, rho, this is second. Okay. And so since these are both one-to-one and onto functions on 1, 2, 3, 4, 5, the domain is going to stay 1, 2, 3, 4, 5. So it's going to look like this. So first, let's think about what 1 is going to end up getting sent to. So 1 is first going through sigma. So sigma sends 1 to 3. And then that 3 now, we are plugging into rho, and rho sends 3 to 5. So overall, where does 1 get sent to? 1 goes to 3, then from 3 goes to 5. So 1 ends up at 5. And there we have it nicely written in. Now we can think about what happens to 2. So 2 comes in and gets sent to 5. And then 5 comes back out. And once 5 gets plugged into rho, rho sends 5 to 1. So 2 ends up being sent to 1. And let's write that nicely. 3 in sigma gets sent to 2, and then 2 in rho gets sent to 4. So 3 trailing through this ends up at 4. 4, remember sigma fixes 4, so sigma 4 is equal to 4. And then when we plug 4 into rho, 4 gets sent to 3. So 4 goes to 3. And last but not least, 5 gets sent to 1. 1 ends up at 2. And so you have 2 nicely written there. And you can see at the end that we have a new reordering of the numbers 1 through 5. And so this is our new function, rho sigma. So it's the function we get when we apply sigma first and then rho. Okay, so let's let Sn denote the set of all the possible permutations on 1, 2, 3, 4, 5. So that would include rho, that would include sigma, that would include rho sigma. We could even do sigma rho. And have all of those would be inside of this set of permutations. Well, the big result for this video is that this set of all the permutations on 1, 2, 3, 4, 5, or 1, 2, 3 up to n, this actually forms a group with this operation of composition. And how many elements are in this group? Well, the number of elements is n factorial. And the proof of this is really pretty simple. So we have, it is closed, as we've seen, because these are 1 to 1 and onto, so really the whole proof relies on these are 1 to 1 and onto functions on our set to itself. And when you compose 1 to 1 and onto functions, you end up with more 1 and 1 and onto functions. And so composing 1 and 1 and onto functions give you new 1 to 1 and onto functions. And so this gives us closure. Functional composition, this is always associative, right? It's always, you do it, it always ends up being the first one you applied first, then you plug that into the second one, then you plug that into the third one. So this is associative. There is an identity permutation, and the identity permutation just sends everything to itself. And this is the identity. It doesn't change anything. And then last but not least, once we have an identity, now that we know that these are 1 to 1 and onto functions, what's something that we know about 1 to 1 and onto functions? 1 and 1 and onto functions, they have inverses. So in particular, once we have 1 to 1, we have an inverse. The fact that it was onto makes the inverse onto the other way. And so permutations have inverse functions. That are also permutations. So these are the inverses are just the inverse functions in the normal sense, and because permutations are 1 and 1 and onto, their inverses are also 1 to 1 and onto, so they are also permutations. Now, how do we get the count n factorial? So let's clean up the board here. So let's think about our possible permutations. So our range is 1, 2, 3, up to n. And let's just go through an order and think about how many choices we have for each one to go through. So how many choices do we have the 1 to go to? Well, 1 could end up in anywhere from 1 to n. So there are n choices here. And then after that choice is made, how many choices then do we have for 2? Well, 2 can go to anything except for what 1 was sent to, because that would mean that it's no longer 1 to 1. And so 2 has n minus 1 choices. 3, now it can go to anything except for what 1 and 2 went to. So it has n minus 2 choices. And we can just keep on going down until finally, when we get to the last one, once we know what 1 through n minus 1 got sent to, there's only going to be one thing left. So when we're seeing how many different ones we have, we're just going to multiply these all together. So I have n choices for the first one, n minus 1 for 2, n minus 2 for 3, all the way down to 1 for the nth choice. Well, what are we really multiplying together here? This is n factorial. And so that is how we are getting our count. So Sn, now that we know that it is a group, we're going to call it the symmetric group on n elements. Symmetric is sort of saying this is all the possible things. If you have n things in space, these are all the possible possibilities of symmetries between them, of sort of mapping them between each other. So for example, we can look at, say, S3. This is 3 is pretty small, so 3 factorial is 6. That's not so bad. So what are the things in S3? Well, there's the identity. It sends everything to itself. We could have 1 go to 2, 2 go to 3, and 3 go to 1. We could have 1 go to 3, 2 go to 1, and 3 goes to 2. And so those are our 2 possible permutations where there are no fixed values. In the identity, everything is fixed. In these 2 permutations, 2, 3, 1, and 3, 1, 2, nothing is being fixed there. And then we could say swap 1 and 2 and leave 3 by itself. We could swap 1 and 3 and leave 2 by itself. And then lastly, we can leave 1 by itself and swap 2 and 3. And so we have 6 different ones here. We know that there's 6 different total that we could have. And so these are all of our 6 permutations. So more broadly speaking about permutation groups, if we have our fixed set A, any collection of permutations on A that form a group in and of itself, it doesn't have to be all the permutations, so some subset of all the permutations that itself form a group under composition, we're going to call that a permutation group. So if we're looking back at S3, well, we need the identity, and then we could do the first 2 permutations we did, where 1 gets sent to 2, 2 gets 3 to 1, and 1 gets sent to 3. And then 1, 2, 3, 1 gets sent to 3, 2 gets sent to 1, 3 gets sent to 2. And you can check here that this actually is a group. That, in fact, if we apply, let's call the second one alpha, first one will be E for the identity. For alpha, if we apply alpha to itself twice, what do we end up with? Well, so 1 goes to 2, and then we plug it in again, and 2 goes to 3. So 1 goes to 3. 2 goes to 3. 3 goes to 1. So 2 goes to 3, 3 goes to 1, so 2 ends up at 1. And then lastly, 3 goes to 1, 1 goes to 2. So 3 ends up getting sent to 2. And you can see that is our 3rd member. And so that is alpha squared. And so this forms a group, because this group, if we apply it to itself one more time, do alpha cubed, 1, 2, 3, alpha cubed would be 1 gets sent to 2, which gets sent to 3, which gets sent to 1. 2 gets sent to 3, which gets sent to 1, which gets sent to 2. And 3 gets sent to 1, which gets sent to 2, which then gets sent to 3. And so alpha cubed is our identity. And so this group right here is just the cyclic group generated by the permutation alpha. Okay, and so this is what would be called a permutation group. It is part of the symmetric group. In fact, it's a subgroup of the symmetric group, but it does not include all of the symmetric group. And so in this exact same way, these permutation groups on A, these are going to coincide exactly with the subgroups of Sn. So if you have some permutation group on the set 1 through n, this is going to be some subgroup of Sn, because it is a subset of Sn, which is a group in and of itself. In any subgroup of Sn, going back the other way, if it's a subgroup, then it is a subset of permutations that form a group, so it is a permutation group. And so this really is a vacuous statement. It's not really saying anything new, it's just saying these two definitions really are the same thing. So one of the goals that we're leading up to, and we are a number of videos away from this, but we are going to show that really deep down any group can be thought of as a permutation group. And so when we say thought of, this is really code for saying is isomorphic to. And so first we're going to give a much better definition of isomorphic than we've been talking about, but you can envision any group that you can make as being some form of a permutation group. And often this is much more helpful in terms of thinking about finite groups and infinite groups, but it is true nonetheless for any group. That is all for this video. In the next video, we will be talking even more about permutations.